So um, this chapter 4 will help us to get into the very important, second important part of this Cal 1. Right? We talk about differential calculus so far, like how to differentiate it and then what does that mean and what are the application of those. And in this chapter 4, we're going to look at how to connect okay, the antiderivatives that we learn in the end of like chapter 3 with the techniques okay, of integrations. How do we connect that? Okay? So it's basically um, this is the beginning of the integral calculus, right? And we will try to connect how the integral differential and integral calculus related in this chapter. Right? So first, what we want to look at is the area. How do we approximate area under the curve, okay, of a particular functions in a certain interval. Right? At this point, we want to put it into a certain interval. So there are a few ways to approximate it. Right? And until the next sessions, when we basically put it a definition that we're gonna an important definition that we're gonna learn, then we will not be able to then we will be able to start precisely getting what the number is, right? What the actual number is gonna, what the actual area is gonna be. So let's say this is a function f, the curve of function f, and I want to find the area between this interval a and b. So one way to approximate is basically break it down this region into many different shape, right? And then approximate with those area of those shape for this area under the curve. And probably that's something that we learned when we were basically in grade 1 or grade 2 when we start talking about the areas and stuff, right? Counting the unit square and so on and so forth. So for us, we want to formulate it to make it easier for us to compute it. So yes, for some of the curve, it will be easier. It will be more accurate if we use a trapezoid, or if we use a rectangle and a triangle in a particular sections, right, to get a better approximations. But for better approximate formulating part, this is what we're gonna be doing. We're gonna try to break it down into rectangles, okay, and using those areas of those rectangles to approximate what is the area under the curve. So when we talk about rectangle, area of rectangle, we need to know the rectangle. If it is a rectangle, it's like this, right? This is how we're going to place it. Then we're going to have what? The length and then the height, right? Or I should say the width and the height. So if we multiply these two, that will give me the area. So what we're going to do is we can break it down into a rectangle in a different shape. Some of them is big, some of them is small, okay, to make it a better approximations. But however, if we do a different shapes, right, a different width, then in the formulating part, it might get into a problem. So what we're going to do is to make it easier for ourselves on the approximations for now, right, we're going to try to make everything in equal width. Every rectangle will be equal width. So let's say if I want to break it down into 6 rectangle, okay, in this interval between A and B. So to make it equal width, then that will look like this. Right? That's approximately equal width. So this width, right, is the same thing as all of them right here. Right? those width are equal width. And what about the height? Okay, and the height is basically that's where we're gonna make a different approximations. So you can see that the first one that I'm looking at is what? The left endpoints. The left endpoint is basically talking about the initial, right? When you're starting with initial interval, like on the left end of the interval, that's where we're going to be using that as the height of the rectangle. So that basically means by doing that, okay, we will have this little part is overestimating. Okay, if I'm using that point. And then the next point right here, if I use the left end point, then the next rectangle, so I'll be overestimating this part. And the next will be right here. So you can sort of get an idea of what's going on. And then the next one, you will have notice that all the red part that I draw it become a rectangle. Those are basically what? Overestimating part. But once you got into after a certain point, that's not the case anymore. So from here, if you look at this, to make it a left end point as your height, and then when I draw it, this will become underestimating. And right here, this will be underestimating now. See that? We are a little bit below of actual the graph area. So what happened is those area, underestimating and overestimating area, they will, neglect each other. And then sometimes you have more overestimating than underestimating, then you will be talking about this area will be overestimated area, right? And then vice versa. So the idea right here is, right, when we are trying to formulating, we are trying to formulating by what? Area of rectangle. And the area of rectangle, to make it easier for ourselves, we're going to make it everything equal width. And when we make it equal width, then the only difference that's going to make us is what? We're going to start from the left end point, or we're going to start from the right end point. So if you take a look at this, right, for the first three rectangle, for the right end point, then this will be what? This will be the first initial point that I'm going to be using to evaluate the same first rectangle. Okay. Okay. And if I'm using the right endpoint, this will be what? Right here. If I'm using the right endpoint, it'll be right here. So notice that using the left endpoint and right endpoint, the estimation part is different. Okay. So that's what we're going to learn in here. How do we formulate these? And then how to use those formula. And another thing that I want to point out is, right, for the first graph, right, I talked about between A and B, right, between A and B, we did it 6 equal width rectangles. And if you make this rectangle more, right, instead of 6, if you make it 12, then the accuracy of, the area under the curve that we are looking for by approximating those rectangles is much better. Because when the rectangles are smaller and the error that you got, right, overestimating, underestimating, the error you got is less and less. This is the idea that we are pushing into for the next session. Okay? So another techniques that we can do is midpoint. So the midpoint is basically, let's say, once again, if I break it down into 3 intervals together, right? 3 equal widths. And the left point is basically talking about your height, okay? The height will be the midpoint of this first, little width increments right there. So when we talk about the midpoint, we're going to be talking about the height we'll be using as the midpoint of this this width. So it will be right here. So therefore, you can see right away, and some portion within this own rectangle, some portion is what? Underestimating, and some portion is overestimating. So it's it become like a more better technique to approximate. So right now I'm only using rectangle. I mentioned it before, there's a different method to do it also, right? But we want to look at this formulating part first. So if I talk about the second, that would be what, right here, right? That would make it a rectangle. And then this is the midpoint right here. We're going to use the height as the midpoint of this rectangle. So in general, technically saying, to make it a good approximation, what happened is we're going to be looking at, depending on where this rectangle is and the height that we're going to be looking for that rectangle is not right endpoint, not left endpoint, not midpoint. It's the best, approximation for this particular rectangle, meaning what is the minimum error that we're going to get. That another way of saying is all the overestimating and underestimating, cancels out each other such in a way that the overestimating or underestimating will be close to zero. So for this rectangle, probably this will be like maybe a better approximation for this particular rectangle, and then using that as a height to do the rectangle. Okay, so that overestimating and underestimating will cancel out each other to a point that close to zero error. So this is the idea of how we're going to be finding out, right, and try to formulating the area under the curve. Any questions before I move any further? Are we all okay with this? Okay. So if you look at this left endpoint. So first, how do we know, how do we find out this equal width right here? Okay, how do we find out this equal width? That will really be dependent on how many rectangle you want to break it down into. Like for example, if you have 1 unit, right, 0 to 1, if you want to break it down into 4 equal parts, then basically each of them will be what? 1/4. Okay. So that really depends on what is my ends going to be, how many subinterval you want to create it. So this subinterval is basically formulated this. We call it delta x, this equal with this width, the increments. That will be basically what? The interval, the entire interval. You're going to break it down into n many what? Subinterval. So that's how we're going to get this delta x for all of them. And once we get the delta x, then that's where we're going to be deciding where is my left endpoint, right endpoints to get my function value. For the midpoint will look like this. If this is x sub 1 and this is x sub 2, then the midpoint, that will become x sub 1 plus x sub 2 divided by 2, which is the average. So we're going to be using this point to evaluate the functions for the height of this particular rectangle. Questions? Difficulties? So as I pointed out earlier, right? The more rectangle that you can make it into subinterval, right? The more subinterval that you can make it, the more the better accuracy you're going to get on approximating the area under the curve. We good? Okay. So let's take a look at on the right end and the left end formulating part. So if you look at the right end part, right, the definition say that the area A of the region S that lies under the graph of the continuous functions f is the limit of the sum of the area of approximating rectangle. So notice that the way that I write it, I mentioned it before. If we make, right, the subinterval infinitely many, that's basically talking about what? All the overestimating and underestimating is very small, such that it will be very close to the actual area that we're going to get. So that's the idea of the limits that we learn when limit going into infinity case. Right? And of course, the limit must exist. So what that basically means is like basically what? Limit as n approaches to infinity of what? The height times with the width, the second rectangle height times with the width. And notice that because we talk about the equal widths, is all of them is delta x, and all the way up to what? N of them. And if n is finite, then we will get approximation. If n goes to infinity, then we're gonna be what? Getting almost exact value. So this is the part that you have to pay attention. If it is right n, right? If it is right n approximations, that means if you have starting x of 0, that's your a, right? And x of n, that's might be the endpoint. If you're going the right n, the very first rectangle, for the very first rectangle, the height of that rectangle, you'll be using what? X of 1 to approximate it, right? Because you're going to be using right n right here, right? So x of 1. So therefore, in the formula, when we are formulating it, this x of 1, that's basically what? Where the n is starting from, when the I is starting from what? 1 through infinity, right? 1 to n. So notice that right here, when we talk about the height, this is what? X, let me use this highlighted. Notice that it's x of I. If you are starting on the left hand side, right? If you are starting from the left hand approximation. So this is my interval, and if you're starting the left hand interval, left hand point as my height to approximate, then you are using what? This x of 0. So how do we write it? X of 0 is basically what? X of I minus 1. The reason why is because on the summations, we started from what? 1, right? I equal to 1. So when you plug it in 1 for the I, right? 1 minus 1 will be 0. So it will be starting with what? X of 0 right here. Okay? But this one is starting with x of 1. So that's how you're going to be formulating for your left endpoint, right endpoint approximations. If it is a midpoint, then that will become the average of between any two subintervals. Right? So as you can see, the midpoint is basically what? X of I minus 1 plus x of I divided by 2. And the delta x, I already explained earlier, the delta x is what? The width of the interval and divided by what? The numbers of rectangle that or subinterval that you want to break it down. Okay. So this is the formula that we're going to be using to what? Approximate the area and the curves. So notice that this is the area for the first rectangle, and this is the area for the second rectangle, and so on and so forth, all the way up to what? Nth many of them if it is a finite. Or if it is infinite, then we're going to talk about that infinite case next time, next session. So, is there any questions on this formulating part? Are we all okay with this? All right. If you don't have questions, then I'm going to move on to the example. Example number 1, we want to estimate the area of the regions between these functions, the graph of these functions, and the x-axis on the interval from 1 through 4. And using n equal to 6. So we want to break it down into 6 subintervals. Here's the first part. We want to use the right endpoint approximations. and we want to use left end approximations, and we want to find out also the midpoint approximations. So 3 different approximations that we want. We good, right? So far. So to talk about left and right ends or midpoints, because of we are basically talking about the same problem in the same interval with the equal subinterval of 6. So therefore, all of these 3, my delta x will be the same. So first thing we need to do is we need to find out my delta x. So in this case, my beginning of my interval is 1. The end of my interval is 4. So to find out the equal width for the rectangle, right, delta x, that is basically what? B minus a over n, which will give us 4 minus 1 over 6. That gives us 1/2. So that basically tells us that each rectangle has a width of 1/2. Another way of saying is from the left end of the interval, you're going to be incrementing 0.5, 0.5, 0.5, 0.5 until you reach it to what? 4. And that increment should be a total of 6 increments. Are we all following so far? So we don't need to graph it, right? All you need to do is you need to look at on the x-axis what is the increments are so that you can put it into a computation. So this is the visualizing part, okay, for us. So here's 1, and then here's 4. We will break it down into 6 sub-interval, and then we want to make it equal sub-interval because that's the easiest for us to formulate it at this point. So because of we make it 6 sub-interval, we know that the increment for each interval is delta x, which is 0.5. So therefore, the next, this is my x sub 0, right? And the next one will be 1.5. This is going to be my x sub 1, and this is going to be 2, right? The increment of 0.5. This was going to be x sub 2, and this will be 2.5. This will be my increment of x sub 3, and 3, that will be increment of x sub 4, right? And then 3.5, another 0.5 increment. This will be x sub 5, and then this will give me what? X sub 6. So a total of what? 6 sub interval. Are we all okay with this? Any questions before I move any further from here? So now, we all good, right? Are we here?
Yes.
Okay. So far okay, right? So far okay. So now, what we're gonna do is we're gonna what? First, estimating the area, right, by using the right endpoint, and for finite numbers of interval case, we will write it down something like this: R with the subscript 6. So that's talking about we are using what? The right endpoint with the 6 sub-interval, 6 equal sub-interval. So according to the formula, because of this is not infinite case, we are talking about what? Summations of I equal to 1. All the way to my n is what? The n is 6 because we want 6 sub-interval, right? 1 through 6. Such that my formula for the area is what? The functions evaluating at a particular I, because we are talking about the right, okay, endpoint. So therefore, this is basically what? The right endpoint right here. So right away, when I is 1, thus will be evaluating at except 1, which is the right endpoint that we want, times with the delta x. Okay? So that is basically what my formula. So computing this, that will become expanding this out, this will become f of, I'm going to write it down every little detail on this, okay, first example, and then after that we're just going to skip some of the notations. So this will be x sub 1 times with delta x plus f of, when I is 1, that will be x sub 1. When I is 2, that will be what? X sub 2. Here's the first rectangle on the right endpoint as a height. Second rectangle, right endpoint as a height. See that? So this is what we're doing. So x sub 2, right, times with delta x, the width again, plus f of x sub 3, right now he's right here, times with delta x. And then continuing this, and then all the way up to what? F of x sub 4 times with delta x plus f of x sub 5 times with delta x, and plus f of 6, x sub 6 times with delta x. So we are multiplying what? We are adding each area of the rectangle, all of this. 1, 2, 3, 4, 5, 6. Okay with that? Any questions? And notice that on every single one of them, the delta x is what? The same value. Right? So basically, we can factor this out. Okay? So after factoring delta x, that basically become, look like this. My delta x times with, delta x is a constant, so I can always factor that out, times with f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub 4 plus f of x sub 5 plus f of x sub 6. So later on, this is where we're going to jump. We're going to jump down to this step and then just plug it in the number right away. So this is what I'm talking about. So this is all the way that we're going to be jumping, starting from the next example. So my delta x is what? 0.5, and times with the functions, the height of the first rectangle using the right endpoint is the function value evaluating at 1.5. The second rectangle, right endpoint, evaluating at 2, evaluating at 2.5, evaluating at 3, evaluating at 3.5, and then evaluating at 4. So these are the height of each rectangle using the right endpoint. So once we compute each one and then multiply, add them up and multiply by 0.5, so this will give us approximately the answer 42.69. And this is the area, approximated area using the right endpoint. Is there any questions before I move any further? Don't have a lot of example. Okay? The idea is pretty much like this is approximation, different techniques of approximating. Okay? So it's like literally like not really like deep concept yet in this case, I will say. So, any questions?
So you just added all of your x and then you multiplied that by 0.5?
Yeah, I added all my function value, right? I added all my function value and then added with this. What is my function value? I basically substitute this 1.5 into what? This function right here. This formula right there. Right? Because the function value right here. So the first one that you're going to be substituting is what? 1.5 to the third power minus 2 times 1.5 to the second power plus 4. So that will give you that will give you a value. Remember, the notation is a function notation, so you're evaluating the functions at 1.5 because that will give you the height. See, because you have what we are looking at is, at this particular x value, then you are basically what? Using the height of the height of the function, which is the height of the function is what? Function evaluating at that particular x. So that height of the function is basically what? Used to approximate for the area of this rectangle. Right? Because the height of the functions will be approximated for what? The height of the rectangle. So when you multiply the width and the height of the rectangle, this gives you what? The area. Are we all okay with this? Any questions? So it's pretty much like, I don't want to draw this. Like, you don't need to draw it either, because if you're going to be drawing this like third degree polynomial, then that will take time, and then it will not tell you, approximation either. So any questions before I move to the next approximations? So you should be able to use your calculator quickly, okay? Because after you punch it in on the first time, then you just need to change the next time that when you look for f of 2, all you have to do is change 1.5 to 2, all of them, right? Whatever you substitute for x. Then that will give you the function value quickly. So you can write it down, those function value, and then add them up. Are we good? Any questions?
One question.
Yes.
Why does underneath the sum sign, why is the I equal 1 for the notation?
Oh, the summation notation is basically tells you your index, where do we start and where do we end. So this is the starting point and this is the end point. Okay.
Okay.
So a lot of time, usually, we want to make it easier for the formulation part. We would start with what? The first one. It's basically that go back to sequence and series that we learned before. Because summation notation is basically the series notation. What is a series? In a sequence, we talk about what? A sequence is what? A sub 1, A sub 2, A sub 3, so on and so forth, all the way up to what? A sub n, that sequence. For example, let me give you the sequence of 2, 4, 6, dot, dot, dot. Right?
Mm.
So that is what? An even number, right? So increment of 2. Are we all following so far?
Yeah.
Right? So what is a sequence? Sequence is a function with the input is only the whole number. I should even say that it would be a counting number, okay? Which is what? 1, 2, 3, 4, 5, 6. You cannot have 0.5, you cannot have 0.2, so on and so forth. Are we all following so far? So therefore, this I sub 1 is basically what? Referring to what? The 1 referring to the beginning of the sequence. And n referring to the end of the sequence. And if you add all of these sequences together, that's called the series, right? Which is, this is a notation for sum of series.
So if the interval is, say, 2 to 4, then the I would equal 2?
No.
Okay.
if you say interval is 2 to 4, the I is still starting from 1. I has nothing to do with the interval. I has something to do with how many sub-interval you want,
Oh, okay.
right? Because you're talking about, for the first sub-interval, you're going to get what? X sub 1 right here. You see that? Right here, X sub 1, right?
Mm-hmm.
So if you talk about, 8 sub-interval, then this will become what? X sub 0 all the way to X sub 8 from 1 to 4. But in the summation notations, the I will be starting from 1. You can change it, but that will be like, all the formula inside will change also. So meaning it's like, if you change I into a different number instead of starting from 1 right here, then this formula will change also. That's the reason why you just wait for a second when we talk about the left end point, which I pointed out earlier right here.
Yeah. I minus 1.
Yeah, because if you want to talk about the left end point, because of your I is 1, then you change what? The sub-interval notation right here differently so that it will formulate differently from now.
Okay.
Does that make sense?
Yes.
Now, it is very important for you guys to clearly know this summation notation, because when you go into Cal 2, the end of Cal 2 is talking about sequence series, sequence conversion, series conversion, so on and so forth. You're going to be using a lot of these summation notations. Okay? We good now?
Yes.
All right. So now let's move to the next part of this example that is asking. Right? So now what I'm going to do is I'm not going to write every little detail anymore. Right now you can sort of see what I'm doing, right? So each part is what? Talking about the area of a rectangle. And this time it's using right end, so therefore what? My height of the rectangle will be using the function value at what? The right end. Okay. So now, next step is example number 2. This time we want to estimate the area of this functions with the left end with 6 equal, which means the height of the rectangle will be using the left end function value of each interval, each sub-interval. So this will become summations of I equal to 1 to 6. Notice that this doesn't change. But however, our formula will change because I want to use the left end. So that means for my first rectangle, right? For my first rectangle, I'm not going to use the right end right here, x sub 1 anymore. I'm going to be using what? The left end, which is x sub 0, to approximate my function. So the height of this rectangle will be equal to a function evaluating at left end. So what happened is that's why we change our formulating part on this. It will be what? X sub I minus 1. Because when I is 1, 1 minus 1 will give me what? 0. Follow? So times with delta x. Now I'm going to skip all of this step, okay? Hoping that we understood what's going on. What did I do step by step? So what do? We will write down the number right away. We know that the delta x for each term that we are adding, each rectangle has the same width. So when we talk about summations, we can factor it out, delta x, so it will be 0.5. And times with this time we are talking about left end, so the first height, right? The height of the first rectangle will be what? Evaluating at f of x1, x sub 0. And the second rectangle, okay, let's say like this one, then we're going to be evaluating, since using left end, the height of that rectangle will be evaluating at what? X sub 1. So the height of the rectangle will be equal to x sub 1 for the second rectangle. Are we all following so far? And then if I have the third rectangle is like this height, if my graph go like this, right? Then this will be what? My left hand point. So I'm going to be using what? F of x sub 2, f of x sub 3, f of x sub 4, f of x sub 5, f of x sub 6. Is that correct?
Yeah, exactly. Or Dawala, the ACH company does that too. And it's actually cheaper on the other
because
side.
6,
Dawala,
you
when
can't put 6, right?
Exactly. You're right. Because look, for the fourth one, the left endpoint is what? Right here, sub 3, right? The fifth one, sub 4, x sub 4. And the sixth one, we are using what? The height as what? X sub 5, right? So if I put x sub 6, that means like I'm including what? Another rectangle to approximate it, but this is already what outside of what we were talking about, right? So therefore, this is what we are the end right here. You can put it into like mole subinterval, but once you put into mole subinterval, and this increment will change also because the formula of the increment is what dividing by the subinterval. So therefore, this is what I have. So if you evaluate, and I notice that a lot of number that we get on the first time when we evaluate it, we're going to be using again right here, right? So when I evaluate all of them and multiply by 0.5, this is what has come up, 26.19. Someone needs to check these numbers. So notice that, there's a big difference on approximations. The same functions, the same interval, right? With the same equal subinterval, but using the right endpoint and using the left endpoint, we got a different approximation. Which one is better? Right? That kind of question will raise up. At this point, it's just approximation. We don't do anything yet. Right? So, are we all okay with this so far?
Right. Let me back that up and say, settlement,
All right. Let me point out something that has something to do with example number 2 that we're going to talk about later on. And notice that by using the right endpoint and using the left endpoint, the approximations of the area is a big difference, right? So why is that happening? Why is that happening? So I pointed out right here earlier, right? Let's use this problem. For this particular function, for this particular graph within this interval a and b, notice that if I use the left endpoint, okay, if I use the left endpoint, I have overestimating is more than underestimating. Do we follow that? So after they they cancel out each other, those estimations, overestimating and underestimating cancel out each other, you're still gonna be overestimating. And another thing that I want to point out right here is this: if you are using the left endpoint, and if the functions, the interval of the function, let me erase this, the interval of the function is decreasing. Notice it from here. Notice it from here to there. The function is decreasing. Then you are basically doing what? Overestimating. But the same function, the shape of the graph right here, look at it. Okay. The same functions. But if you are using the right endpoint, okay, if you are using the right endpoint, and notice right here, on the decreasing interval, if you are using the right endpoint, this is what? Underestimating. So, left endpoint and right endpoints, how is your values going to go? It really depends on the functions will be increasing or decreasing how much. That will make it overestimating and underestimating a lot difference. Are we all okay with this? So vice versa, if you see that if you're using the left endpoint, the function is increasing, then we will be underestimating. But however, on the right endpoint, if the function is increasing, then we will start doing what? Overestimating. We will start doing overestimating. So that basically tells me when we look at
Oh, yeah. The settlement
this
are already
area
happened, right? They're
using the
already
right
paying
endpoint,
out. Yeah, that's what I
and
mean.
our area is 42.69. So that basically tells me like within this interval 1 to 4, the function must be increasing interval. Okay? It could be increasing interval. Just by looking at this value, we will not know. But by looking at the right endpoint and left endpoint, comparing it, and then what I pointed out earlier, then you can sort of predict that hey, within this interval, probably this is increasing interval, because we can see a big difference right here. Right? Because if it is increasing interval, then if you're using left endpoint estimation, that will be what? Underestimating. But as in the right endpoint estimation, it will be overestimating.
Yeah.
Yes, no? Are we all okay with this? Follow my point? So, let me point this out right here. Anytimes you are, let's wait for example number 2. Then I'll point out. Let me finish up this one with the last one, which is the last part is asking you to use the midpoint formula. So when we're using the midpoint formula with 6 subinterval, there will be summations of I equal to 1 to 6 of f of x sub I bar times delta x, where x sub I bar, that is basically what? X of I minus 1 plus x of I divided by 2, right? The average. So, I made a mistake right here. I didn't mean to put x of 1, x of 2. I want to put down the value. Okay? I want to put down value to make it short for you guys to write it later on. So this will be 1, 1.5, 2, 2.5, 3, 3.5 right here. Make sure you change that, okay? I made a mistake. So that way it will help you to write short. So 0.5, and then the first one is the between 1 and 1.5. So you take the average, which will give you 1.25, right? You add 1 plus 1.5, 2.5 divided by 2 will be 1.25.
Yeah.
And then the next one, you find out the average. Don't really need to, because we know the increments already, because each increment is what? 0.5. So therefore, the midpoint will be increment by 0.5 also. So it will be the next rectangle will be 7.5. The next rectangle, the height of the next rectangle will be 2.25. The height of the next rectangle will be 2.75 and 3.25, and last one will be 3.75 to evaluate. And when you evaluate it, this will give us 33.04 if you use a calculator. So now you can see that, in my opinion, the midpoint approximation should be a better one, because when you use a midpoint approximation, within the rectangle, it has overestimating and underestimating already. And then you basically try to cancel it out as much as possible already right there. So the error is much less. So any questions on this example?
Sorry, I was plugging the numbers into the calculator and missed how you got the 1.5.
1.5?
Well, like in the for your function values, like you got for the midpoint, your first value for f is 1.5. 1.25, sorry.
1.25, no, not 1.5. 1.25.
Yeah, uh-huh.
Yeah, so my
I'm saying I missed that. How did you get? Where did you get
How-
1.25 from?
How do I get that?
look, the email
Where
It's
did you get
basically, if you look at this right here, the rectangle,
general things we need, right?
if you look at this first rectangle right here,
Uh-huh.
right here is 1,
Oh, you're
right here is
getting
1,
the.
right here is 1.5, and we are looking at what? Using the midpoint as the height right here.
Mhm.
So to get this height, that's basically what? Using this average right here, 1.25.
Okay.
Right? You plug it in this into a function that will give you the height of the function.
Yeah, basically.
And then you do the same thing for what? The rest. Are we all okay with this? Any questions? So, in my opinion, I don't think this is a really complicated concept. Okay, but you just have to be careful on the computation part, and then understand the differences between, like, approximations, right endpoint approximation, left endpoint approximation, midpoint approximation. And once you go into Cal 2, like, you're gonna learn like trapezoid method and Simpson rules and stuff to approximate these intervals, these like area. Right? Okay, now can I move on to finish up this section? Any questions before I move away from you? All right. So this is something that I want to point out earlier, but I will talk about it now. Right? This is another way of estimating by upper sum and lower sum. Estimating by upper sum and the lower sum. So what does it mean by upper sum? What does it mean by lower sum? Upper sum is basically entire interval you will be always overestimating, using the overestimating part. So therefore, by saying that, right here, see, yeah, let me just draw it so that you can see better on the information. So let's say if you have a function like this, right? And here's the interval a to b, w1. If you want to talk about upper sum, we want, in that interval, we always want overestimating. So that means when you break it down into rectangle, right, then you need to do overestimating. So for the first rectangle, I'll be using what? The left end. And for the second rectangle, I'll be using also the left end, so that it will overestimate the rectangle. But for the third rectangle, I will be using the right end to make sure that I overestimate. So this is called upper sum estimation. Are we all following so far? For the same interval, if you want to do lower sum, then what's going to happen is we're going to be making sure that everything is what? Underestimating. So therefore, for the first rectangle, I will be using the right endpoint. For the second interval, I will be using the right endpoint also. And the third interval, I'll be also using what? Crap. How about that? So for this one, you can see that I'm using the right endpoint. But for the last one, I will be using what? The left endpoint. So notice that this point is used the same for what? These two rectangles. So notice that right here, all my rectangles are what? And the estimate. So this is called the lower sum approximation.
Yeah. That was very clear.
Are we all following so far?
That was very
So in this kind of situation, there is no formula, but we need to, a lot of times lower sum and upper sums like harder to approximate if we have like
no, but I mean,
if we don't have a program that we know how to write it down, right?
the settlement has to be.
Or if the graph of the function is like really nasty one on a certain interval, we can't really graph it, then we won't be able to see where the breakdown points are, increasing and decreasing. You can sort of do it, but like how can I say, like use the first derivatives and then find out where the first derivative value will be greater than 0 and first derivative values are less than 0. So that will tell you whether it's the increasing interval and the decreasing interval, and making sure that your increments are exactly in them so that you have a better approximation. But I just want to point out the idea, so I'm giving you an easier function to look at it. So let's take a look at on the situations. Giving you a is 1,
I gotta talk to you about that a little bit too, because like I'm not.
a is negative 1, my b is 1, right? And my n is 4, so my delta x will be b minus a all over n, which is 1 minus negative 1 divided by 4. My n is 4, so which is going to be 1/2, 0.5. So now I want to take a look at right here. This graph is easy enough to graph. That's why I'm saying you can sort of look at this. So 1 and negative 1. And this is a parabola opening upward and then shift up 1 unit. So right here 1, 1, and 1. And this is the curve that we are getting. So, and our endpoint is right here. Right? That's my interval from 1 to 1. And what do we want? We want to put it into what? 4 equal parts. So if I make it 4 equal parts from the graph, right? So that's what I'm saying. The graph is easy enough such that I don't really need to look for the increasing and decreasing interval. Right? Because if it is a decreasing interval right here, right, from negative 1 to 0, then I'm going to be, since this is a 0.5, that will be negative 0.5 and 0, 0.5. Let me put those. Then to make it upper sum, I have to use what? The left end point. You can see that right here. Right? So only if it is a left end point, then it will be upper sum. Only if it is the left end point, this will be upper sum on the decreasing interval. But when it changes into increasing interval, then you need to use the right end point to make sure that it is what my upper sum is using the right end point. Okay. So this point, so my right end point. See that? And this rectangle will be right end point. So that's the first example that we're going to do. So when we find out the area using the upper sum, and that will be 0.5 is my delta x times with my function will evaluate negative 1, negative 0.5, right? Because these two, the first rectangle and the second rectangle is using left end point. And the third rectangle and the full rectangle is using right end point to make it overestimating. So that will be these. And when you evaluate this, this will be approximately equal to 3.25. I got exact value. So that is for sure is overestimating of the original area that we have. Are we good? Okay. So now what happened is the same right? The same
It's obvious
graph,
that they're not going to get the help from the government.
the same graph,
They will,
but this
but
time
they're not.
we want to do a
Honestly,
lower
getting
sum.
a fucking $1,200 stimulus check for anybody is like
I
one of
want
the
to do
last.
a lower sum.
Oh god, that would have been fucking hilarious. Oh god. Yeah. Oh, yeah.
So when we talk about the lower sum,
And they're already listing, they're already high risk. All the people have these fucking things, right?
for the same graph,
Oh, my God.
then that changes. First rectangle for the lower sum, this will be the point. The second rectangle, the lower point, this will be the point. And for the third rectangle, this will be the lower point. So the same number we're going to be using twice. And then the fourth rectangle, it will be what? The lower sum will be this one. So my computations for lower sum will be the area is equal to 0.5 times with a function evaluating at negative 0.5 plus the function evaluating at 0.5 and then plus function evaluating at 0.5 plus the function evaluating at, oh, did I miss it? Yes, I missed it. It's not 0.5, 0, 0, and then 0.5. See? Because this rectangle uses 0 as approximation. This rectangle uses 0 of the, as the height of the, to find out the function value for the height. So when you evaluate this, that gives you 2.25. So the area, clearly this area is underestimating, and this area is overestimating. So that's basically the lower sum and upper sum.
Yeah, but 3, and then here's the question, is 3 for what? Right, I mean,
Any questions on
that's
this?
yeah, 3 months with full deficit, right? But like, right?
So it's just computation.
Right, yeah, but here's what I.
Let's stop right
what I would
here.
do,
Let's take a
what would
break.
be required, even if you said tomorrow, like, let's start
And then